Hello guys, so today we're going to be talking about our review of this week's class, which was February 3rd through the 5th. Okay. We were finishing up Chapter 3 talking about chairs and boats, cis and trans for different conformations in the chair form, and then we're going to start Chapter 4 and finish Chapter 4, which is essentially free radical halogenation. Alright, so last time we left off talking about chairs and boats where you can have some chair conformations that are worse than others due to the 1,3 diaxial interaction, right? So that interaction and this interaction, which would be equivalent to something here. If that's axial, this would be equatorial, this would be axial, so it would look like that. Right? I feel like it wasn't as clear in lecture about how this relates to this. Remember, when you draw a chair, right, something like this, right, chairs are drawn with lines. So axial, 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 and equatorial, 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 equatorial. I believe this one goes equatorial, equatorial, right? So it should be drawn like that. You should not be drawing something like this. If you draw dashes or wedges, right, that's wrong. Please do not do that. And that's because dashes and wedges are a way to give three-dimensionality to a two-dimensional image. Right? We know cyclohexane is not flat, but we want to specify the relationship between groups that are on cyclohexane with dashes and wedges. So if I draw something like this, and I say, give me the name, it's a little ambiguous, right? You could say 1,2-dimethyl cyclohexane, but that doesn't specify the relationship between these two groups, right? Are they cis or are they trans to each other? If I just give you the name 1,2-dimethyl cyclohexane and I say give me the structure, cyclohexane, there's two structures that you could draw, right? There's ambiguity involved there. You could draw the cis one, where they're both axial, or you could draw, you could draw the trans one, where they're both axial, since it's 1, 2, or you can draw the cis one, where one's axial and one's equatorial, right? So both of these would technically match the name 1,2-dimethyl cyclohexane. So to specify which one I'm talking about, we have to tack on cis or trans, because we're talking about the relationship between two groups. If I said cis, then I specifically would be looking for this group. And how do I know that? Because this one points up, and this one also points up. What do I mean when I say up? I mean if you take this three-dimensional molecule and you smash it down, and you make the model yourself to prove it to you, this would go up, and this one would both point up, right? That's what I mean when I do the up is axial, up is a wedge, up is equatorial, up is axial, up is a wedge, up is equatorial, dot, 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 right? That's what I'm talking about. I'm talking about if you smash it down, which way does the group point? Does it point up or does it point out? Okay, so last time we left off talking about saying, well, what happens if there's multiple groups attached to our cyclohexane? What if the groups are really big, right? So suppose we had two T-butyl groups. So this would be cis-T-butyl. So if I wanted to name this cyclohexane, they're at the 1 position, at the 4 position, and since it's a wedge, I say up is a wedge is axial, up is a wedge is equatorial, up is a wedge is axial, up is a wedge, it's equatorial, right? So axial, equatorial, axial, equatorial. So what I'm talking about here is when I say up is if I smash it down, which way will it point, right? The axials will point up, the equatorials will point up. The axials will point up, the equatorials will point up, and they will alternate. So if I smash it down, these will both point up, even though one is axial and one's equatorial. And so since they both point up, this would be the cis. The positioning is 1 and 4, and they're both T-butyl groups. So I use di because there's two of them. Di-tert-butyl, and I'm actually not completely sure about this, but I think it goes di-T-butyl because the name of the group is T-butyl, so it gives you like this dit in the middle of the word. It looks weird. Cis-1,4-di-T-butyl cyclohexane. Okay, so there will be our name. And if I said draw the most stable conformation, right, if you draw a chair, you say, okay, well, chairs are more stable than boats, so I'll draw a chair. One of them will be axial, so give me that. One of them would be equatorial, so it'd give me that. And that's my answer, right? It turns out for this specific molecule, and other molecules that have really big groups in the cis 1,4 position, that this guy has a really bad 1,3 diaxial interaction, right? This interaction, because this T-butyl group is so big, that interaction is really bad. So if you do a chair flip, you just get the opposite problem, right? You get the, well, excuse me, you get the same problem, but with the opposite group. You get this group becoming axial, and you get the other group becoming equatorial, but that doesn't solve your problem, right? You still have the cis 1,3 diaxial interaction. Bad news. So what the groups do that are big, like T-butyl or bigger, is that they actually force the boat, right? It just turns out to be the case that the boat, I did not draw a squiggly line, come on computer. The boat is more stable. Oh man, it's pissing me off, right? So what it does is it says, okay, I'm T-butyl, I'm so big, I'm going to steal the axial position. And the other one says, well, I'm T-butyl, I'm big too, I'm going to steal the axial position. And it forces the 1,4 diaxial interaction to occur, right? That's so annoying, stop that, right? It makes it look like I'm a 4-year-old trying to draw cyclohexanes, right? This 1,4 diaxial interaction is really bad, but the T-butyls force that to happen. The only way that the molecule can kind of compensate for this really bad interaction is to draw what I call, or what is called, I should say, the twist boat. And I don't know if you'll be able to see it the way I'm drawing, especially with this broken software. Let me try again. So we'll go. Oh man. I don't know why. Apparently drawing on the right side of the screen makes my drawing look squiggly, so let me try a different side. No, that's ugly too. Okay, so it's not so easy to draw, but I will draw it. I can do this. Let's see. We want one to go this way, and then that way, and then down a little bit, and then crisscross, and then up, and then up. There we go. That's a twist boat. A little bit of a bow tie, right? So one of the groups kind of points back in space a little bit, and one of the groups kind of points forward in space a little bit. So T-butyls still get their equatorial positions, but now this 1,4 diaxial interaction is offset a little bit because the boat is kind of twisted, right? So if you take and you make a normal boat, right, and then you take this one and push it away from you, and you take this one and you pull it towards you a little bit, that would be the twist boat. Now it's a little bit hard to see in 2 dimensions, but if you make the model, you'll see what I'm talking about. So when you get large groups in a cis 1,4 configuration, you can actually form twist boats rather than a bad chair or the other bad chair. Okay. So last time, like I said, what happens if we have multiple groups attached of different sizes? I'll take the methyl group and the ethyl group and say draw the lowest energy conformation. Well, the lowest energy conformation is going to be a chair, since we're not talking about 1,4. Twist boats out of the question. So let's start off by drawing a chair. Say, I always like to just define the top position as 1. Here it doesn't really matter. This would be 1 because it's an ethyl, so 1, 2, 3. So at position 1, I want this one, the bigger of the groups, to be equatorial. So I'll do it the way I normally do. I'll do up, which is a wedge, is axial. Up is equatorial. Up is axial, right? And since I'm talking about wedges, we know that one can be axial and the other can be axial, so I'm labeling as I go along, and that says, okay, I put one position axial, CH2, CH3. I put 3 position axial, so 1, 2, 3, I'll put it here. That will also be axial, CH3. Now I have the correct relationship to these groups. I have the correct relationship of the groups to each other. Now I evaluate the conformer and say, should I do a chair flip? And very clearly the answer is yes, right? So if I do a chair flip, I go from having 2 axial groups to 2 equatorial groups, where the ethyl will be here, the methyl will be there. So this would be our correct answer, the lowest energy conformation. Okay, try one more. If I take and I draw isopropyl, I'm going to use the subscript IPR for isopropyl. IPR is equal to that, right? And then we have a methyl on the other side. Draw the lowest energy chair conformation. Same thing. First draw a chair. Okay. Say up is a wedge, is axial. So I'll start by defining that. So up is axial, up is equatorial, up is axial, right? But this is not up, it's a wedge. It's a dash, not a wedge. So up is axial, up is equatorial, up is axial. This will actually be equatorial as well. So if I put isopropyl like that, then 2 carbons over, right? 1, 2, 3. I would have to put something in the equatorial position. So 1, 2, 3. That would be axial, that would be equatorial, that would be my methyl group. Is that the lowest energy conformation? No, it's not, because the bigger group is in the axial position. We want the bigger group to be in the equatorial position. And so I do a chair flip, which converts my equatorial group now into an axial group. And now this would be the lowest energy conformation. So in lecture, I believe I asked you guys to do this one. You might already have done it, but good practice. Do it again. If you missed lecture or whatever, pause the video, do this on your own. I'm not going to give you the answer here. I'm just going to say, draw the most stable conformation. So chair, boat, twist boat, and where the groups go. Okay. Moving on, I just wanted to have a brief note. So I'll just kind of draw a box. I'm going to mention that this exists. I'm not going to quiz you on it. Just letting you know that it happens. You can fuse rings together, so you can have bicyclic compounds. Right? Bicyclic compounds are named with the prefix bicyclo. So you just take the total number of carbons, which is 6, 7, 8. So octane will be our name. But this is not just regular octane. This is octane mutated in such a way that it's forming two ring structures. One's this ring and one is this ring. So the way that we do it is we say, well, it's a bicyclo compound. And then in the brackets, we say how many carbons are on one side. Well, there's 4. How many carbons are on the other side? There's 2. How many carbons make up the bridge between these two carbons, right? By default, there will be 2 carbons that connect. If there's more than 2, we specify that. So if there's not, we just specify it with a 0. So that'd be 4, 2, 0, bicyclo 4,2,0 octane. Right? If I did, what structure I do in lecture, I did one of these. Oh, do not. Well, I don't know why I can't draw on the right side of the screen. Maybe it's the orientation of my body or something. I'll try. Something like this. Yeah, maybe it's just the way that my hand is. There we go. That's supposed to be like that. Okay. So I have a 5-membered ring that traces the dotted line here. Right? Everyone sees that 5-membered ring. But in that 5-membered ring, there's another 5-membered ring. That's the dashed line. Right? That goes here. So I kind of have 2 5-membered rings that are smooshed together. If I was to draw this in a flat orientation, I'd get something like that. This would be bicyclo. I have 3 carbons on one side, right? So there's 3 carbons there. I have 2 carbons on the other side. And now the 2 carbons that are bonded together have a carbon in the middle, specifically that one, right? So now it's bicyclo 3, 2, 1. And how many total carbons do I have? 1, 2, 3, 4, 5, 6, 7, 8. So octane. Okay. So like I said, I've just mentioned that it exists, and then moving on from there. So that's the end of chapter 3. Time to start chapter 4 and actually do some chemistry. Yay, chapter 4. Radical reactions. I really think that chapter 4 can be boiled down to mechanisms and free radical chlorination, bromination, and then carbocation stability and the inductive effect. So I mentioned a little bit of kinetics and thermodynamics. It's good to know, but it's not imperative, super crucial. So, all right. So chapter 4, like I said, is essentially mechanisms. What is a mechanism? How does it work? Mechanisms. I'm going to say free radical. I'm going to say halogenation, right? Meaning you can add a halogen on. Halogenation. And then I'm just going to summarily say inductive effect, right? That'll take care of our carbocations, carbanions, and free radicals. That's kind of what you can boil down chapter 4 to, in my opinion. Alright, so remember, the mechanism is a way that we draw arrows in organic chemistry. It's a step-by-step process that says exactly what is happening with no ambiguity. Right? So in the nice acid-base chemistry of a strong base with a strong acid, we get something like sodium hydroxide interacts with HCl. We take the arrow starts at an electron source and goes to a very specific location, to the atom it's making a bond to. Hydrogen is not allowed to have more than one bond, and so the electrons between the hydrogen and the chlorine have to break and go to the chlorine, both of them, so it's a 2-headed arrow. That gives me a molecule of water and chloride. Okay. So this is the mechanism by which this occurs, right? Without the arrows, it would be, so if I just draw this, that's the reaction, and if I say draw the mechanism, which I will be saying many times, you would have to draw that, right? step-by-step process. In a simple case, 2 arrows, no big deal. But what about if we did something a little bit more complex? So suppose we did the free radical chlorination of methane. So methane plus chlorine under ultraviolet light to give you 1-chloromethane and HCl. Right? Now it's not so clear. So this would be the reaction. That's how I like to do it. And then underneath, we draw the mechanism. In this case, it's a radical mechanism. How do I know it's a radical mechanism? Well, because I'm teaching you it, and I already know these things. If I were you, how would I know? Stop that. If I were you, how would I know that this is a radical mechanism? Usually, this is the clue, right? For a lot of chemical reactions, you can kind of look at what the chemistry is, what products are being formed, what reactants are being consumed, what intermediates are being used, etc., and you can get a clue as to what type of mechanism it is. It's not always true, but sometimes it'll give you a hint. HV typically means there's a radical going on. Why? Because HV, H-nu, is ultraviolet light. It's light that's needed to homolytically cleave a bond, cleave a bond and give you some type of radical species. And that's exactly what we're going to do here. So in a radical mechanism, radical mechanisms have 3 steps. They necessarily have an initiation step that gets it started. They necessarily have a propagation step, which keeps the reaction going over and over and over again. And then eventually, they also have a termination step, which ends the chemistry. So if I ask you for a free radical chlorination of methane mechanism, you have to draw all 3, and you have to specify which reactions are part of which. So the way I like to specify is by saying initiation, underline. So initiation is the chlorine-chlorine bond gets hit by ultraviolet light. 1 electron goes to 1 chlorine. The other electron goes to the other chlorine. So remember, I'm using the half-headed arrows now. And that will give me 2 molecules of chlorine dot. That's all it is for the initiation. Couldn't be simpler. Right? The propagation step is where things things get a little bit more complicated. There's a couple more reactions. So you'd say propagation. Chlorine dot from the previous step interacts with the molecule, in this case methane. Of course, there's other carbon species I can choose. 1 electron makes a bond to the hydrogen. Says, give me your hydrogen. I don't want to be chlorine dot anymore. And carbon, being the weak little wimp that he is, says, okay, I'll just do what you said. He gets the other electron. This generates your HCl from above. Right? Remember before we did HCl, that's where that comes from. And what is left over? A molecule of C dot, right? The methyl radical. The methyl radical then interacts with a molecule of the chlorine, not another molecule C dot, but the chlorine, because there's lots of this around relative to the amount of C dot that is around. It says, hey chlorine, you want to make a bond? And chlorine's like, yeah, carbon, you're cool. He's not so cool, but chlorine doesn't know that, right? And that's how you form your product. Your chloromethane, and conveniently, another molecule of C dot. This molecule of C dot then just floats around until it finds another molecule of methane, which gives you a C dot, which floats around until it finds another molecule of chlorine, which gives you another Cl dot, and round you go, hence the propagation step. So one way you could tell if your propagation step is correct is to say, is the product that I'm generating in one reaction the reaction of the next, and is the product of the second one able to go back and be the first one. Now in a 2-step propagation step like I have here, that's nice and clean. You can have 4, 5, 6-step propagation steps. We're not going to worry about that just yet, but we might see it in the future. Hint, hint. Okay. Eventually, sometimes bad things happen, like I can't draw for whatever reason. Seriously, pen? And the termination step. Hold on, I'm going to pause the video real quick. Alright guys, sorry I'm back. I had to pause the video so it'll be a little disjoint, having technical issues. Anyway, occasionally when you have 2 radicals or many radicals floating around the solution, they can find each other, and when that happens, you get the termination step. So termination colon, underline. You can have 2 of the carbon radicals find each other. Again, this is just random. So radical, radical. Things are floating around. You don't really have good control over what's happening. Kissing arrows. Mwah. And you get a molecule of ethane. Other possible termination steps, of course, whenever you have the initiation step, you can have the reverse initiation step, where two Cl dots come together and say, hey, you know what, this sucks, let's actually bond. And you get something like that. Or you can get something like C dot interacting with, instead of a molecule of chlorine, rather chlorine dot, and you get one more molecule of the product, but you don't generate any more radicals. Right? So all of these are different termination steps. If you get creative, sometimes you can think about other termination steps. You can get rearrangements and things like that. We're not going to go too in detail with it. What I care about is, can you recognize the initiation step goes from having no radicals to some radicals. The propagation step goes from having some radicals to some radicals, and you regenerate the reactants of the other initiation steps. Right? And the termination step goes from having some radicals to no radicals. Right? The product of a termination step should not have any radicals, or at least the total number of radicals in that reaction should decrease. Right? So if you go from 3 radicals, you can go to 2. That would count as a termination because you're killing one of the radicals off. All right, so that's our general mechanism for free radical chlorination. What we talked about in Chapter 4 was that it's not always just that simple. All right, so let me go to where I'm at here. All right, so suppose I gave you an example of free radical chlorination of this molecule, methylcyclopentane, and sometimes you'll see it written like this instead of like plus Cl2. Doesn't matter, just different ways to write it. I actually prefer to write the reagent that's reacting on the top, although I wouldn't say it's wrong to do otherwise. So I like to draw it like this. All right, and there's different products you can create, right? You can create the chlorine here. That would give you this product. You can put the chlorine here. That will give you this product. You can put the chlorine here. That will give you this product. And you can put the chlorine here. That will give you this product. Right? Again, the right side of the screen is weird for some reason. Right? Which one actually happens? Well, to answer this, we need to know a thing called the inductive effect. The inductive effect is essentially carbons donating electron density through sigma bonds. It has to be through the sigma bond. They do this because carbons will communicate and they like to share with each other. So let's think about the mechanism, right? This is what you should be able to do when you see a reaction. So suppose I gave you this question on the test. I said, here's the reactants, draw the major product. What you should do is first say, okay, this is free radical chlorination because I'm using chlorine and ultraviolet light. That means it'll be That means it will be a radical mechanism, which means I'll be forming a carbon radical. The most stable species of the carbon radical to form, per the inductive effect, will be the radical that looks like this, the tertiary radical. And therefore, when I form the product, the chlorine will bond to the tertiary radical position, and so the major product that I form will be this, and this will be, this will be the answer. Oh yeah, I forgot I can do that. This will be the answer to the question, so this should be the structure I draw. Notice, you don't necessarily have to draw anything. Maybe you draw this. If you can't keep all those things straight in your head, that's okay. Although ideally, when you take a test, you should be able to keep all those things straight in your head. That's the logic that you want to follow through in order to answer questions on a chemistry or on my organic chemistry test, right? You should think, okay, this is what I know. This is the mechanism that it goes through. It forms this structure. This is the most stable of the structures because of the inductive effect, so you have to know and understand that. And then you say, therefore, the corresponding product will be this one. Right? So the inductive effect says that carbons donate electron density through their sigma bonds. So what that says is essentially that this structure is more stable than the secondary structure, which is the same stability for all intents and purposes as this structure, which is more stable than the primary. So this is tertiary, this is secondary, and this is primary, right? So this carbon has 7 electrons, he's a radical, but he's got 3 buddies that help him out. Say, I understand you only have 7 electrons, I'll share some electron density through my sigma bond with you, so you kind of have like 7 plus electrons, right? 7 plus plus plus, because you have this little bonus from your buddies. This one over here, he has the same effect, but it only happens twice. He's only got 2 buddies to help him out. So he's like, well, I understand you have 7 electrons, but you have like 7 plus plus electrons. And the same thing here, you have 7 plus plus. And eventually this guy has 7 plus, so he's not as good, right? They want 8. 7 plus 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 is closer to 8 in terms of the language I just made up right now on the spot. So it just kind of helps justify the inductive effect. The same trend holds true for carbocations. So if I were to magically just turn the structure into a carbocation, secondary is better than primary, but tertiary, let's see, primary is this one, right? So tertiary, secondary, primary, same argument holds true. Oh, you only have 2, 4, 6 electrons. I'll help you out using the inductive effect and help stabilize your positive charge. So the energy of this positive charge goes down a little bit because there's a little bit more electron density around this carbon than there would otherwise be, thanks to the inductive effect. Okay, so that's what the inductive effect is. That's how we want to think about it. That's how we want to be able to use it and also understand the mechanism in order to actually answer my question, which is, what is the major product? And you can just go directly from looking at this, thinking about everything we just said, and then drawing the structure. Okay, let's name this, by the way. How do we name this, right? To name halogens, I'll redraw the structure because we're running out of space. To name halogens, we name the same way we name the alkanes, right? We find longest chain, we number so that the substituents are at the lowest positions. We just turn fluorine, U-O-R-I-N-E, fluorine turns into fluoro, U-O-R-O. Chlorine turns into chloro. Bromine turns into bromo. And iodine turns into iodo, right? Not iodino, but iodo. Okay, I'm not gonna, whatever, you can figure it out. So we count the longest chain, 1, 2, 3, 4, 5. So we're talking about a cyclopentane, that's our parent name, right? At the 1 position, what do we have? We have a chlorine, and at the 1 position, we also have a methyl. What comes first? C for chloro, or 1 for methyl. Hopefully we all know 1 chloro, 1 methyl, cyclopentane. That would be our name. Okay. If I had one of the other structures from before, like that one, we say, oh, we have a 1 here, we have a 2 here, or we have a 1 here and we have a 2 here. Which one's right? Try again. Which one's right? The substituent that comes first alphabetically will be first, since the size is the same. So we have chlorine versus methyl, C versus M, so we should number 1, 2. So we have a 1 chloro, 2 methyl, cyclo, and I ran out of space, pentane. Okay, so we can name halogens just the same. So a very common question will be maybe something like this, like HV and Br2, and we'll give you 2 bromo, 2 methyl, 2 bromo, 2, sorry, this is getting ugly, let me just try this one more time. 2 bromo, 2 methyl butane, and I'll say draw the starting alkane, right? Well, in order to solve this, you say, okay, 2 methyl, 2 bromo butane looks like this. Butane is 4 carbons. At the 2 position, 1, 2, I have a methane. At the 2 position, 1, 2, I have a bromo. Oh, how do I make this? From free radical bromination, that means I have to make this structure, C dot, which means I just have to have that structure to start with. So that would be the answer to the question. You want to be able to go forwards and backwards. Okay, so that takes care of some of that. A little bit of a difference between chlorination and bromination. Chlorination is not necessarily specific. So for example, if I said free radical chlorination of propane can give you this, can give you that. Turns out that the amount of product that you get is about 60% of the 2-chloro to 40% of the 1-chloro. But if I do the same thing with bromine, it's a very different game. With bromine you get 99% that and 1% that. Right? Bromine is essentially very specific. Bromine always reacts at the tertiary position. Why? I'm talking about primary hydrogens for chlorination. It's about speed of 1x. Secondary is about 4.5x, so 4.5 times faster than the primary. And the tertiary hydrogen is about 5.5x. So, 5.5 times as fast. Not bad. You kind of get a slew of things. In the bromination game, completely different. If hydrogen is 1x, the secondary hydrogen for bromination is 220x, right? It's a huge difference. Huge, huge, huge. And the last one is the tertiary hydrogen is 19,400x, right? It's not even a question, right? This guy is hands down the winner. It's like Michael Lewis running against me in a 20-meter sprint. It ain't gonna happen, right? At least not now. Maybe in my college days, I'd give him a run. Whatever. Okay, anyway, so bromination is specific at the tertiary position. Chlorines give you a slew of stuff. Later on, when we're actually using these compounds to make other products, synthesis and stuff like that, sometimes we won't care where we chlorinate. We just need a chlorine on there. That's all we need. Then we could use free radical chlorination. But if we need it to be at a specific location, then we'd have to use bromination. Okay. One other way to brominate, I guess I said this as well, is called NBS. NBS is N-bromosuccinimide, which is a molecule that looks like this. And it does very, very same thing that Br2 does. It does homolytic bond cleavage to give you a Br dot in the presence of HV. Right? It gives you Br dot, and then it gives you resonance stabilized N dot, which is why it's used, right? Because that resonance, this has lots of resonance contributors, so essentially it can float around in solution, stable, and you don't have to worry about it. It just provides bromine dot into solution, the same way Br2 and HV does, but because it only gives you one molecule for every homolytic bond cleavage event, you have essentially half the concentration that you generate here. Sometimes reactions are very sensitive to radical concentrations, and so there are some cases where NBS is useful. Of course, you still have to have HV. NBS is useful. In some cases, it doesn't matter, and then you can use either one. So just want to let you know you might see both, and you will see both. Okay, so that takes care of that. That's our free radical chlorination and bromination. And then there's one last thing to consider, and that's more than the inductive effect, but the resonance effect, right? So suppose I did free radical chlorination of this molecule. What would be my major product? Go ahead and pause the video and try to figure it out. Alright, hopefully you've unpaused the video, and let's see what you get. Hopefully you drew this as the major, and if I asked you to draw the minor, what would you draw? Hopefully you drew that. What should be the logic that you're using to decide this? So you say, okay, I'm starting out with 1, 2, 3, 4. It's called 1-butene, but we'll worry about the nomenclature later. We're going to do free radical chlorination. I know that because I'm using Cl2 and HV. That tells me that I'm doing a radical mechanism. In the propagation step of the radical mechanism, I'll be extracting the tertiary hydrogen first. Oh, there isn't one. Okay, then I will extract the secondary hydrogen. That will give me a C dot that looks like this. Wait a minute, that's resonance stabilized, and that's the important thing here, where this electron can go here, one of these can go there, and one of them can go there to give you a structure that looks like this. Now, when this molecule reacts, it can react at this position to give me the major product, or it can react at this position to give me the minor product. Why is it necessarily the case that this one is major? Because this is a secondary radical, and this is a primary. Per the inductive effect, since we already took care of the resonance issue, which one is better? Secondary is better, and so it will react more. More of this will form, and so the major will be this one. Right, that's the logic, the line of reasoning you want to be able to go through with minimal writing of things down. Right, you should be able to do all that stuff in your head. If you can, then you're in good shape for the exam. If you can't, you probably still have some more studying to do. Okay, Take a look at bromination. So I can give you a molecule like this and say, let's brominate it with Br2 and HV. HNu. Right? Go ahead and pause the video, think about the mechanism, and tell me what the major product is. Hopefully you've unpaused the video and you drew this. Should there be a side product? Essentially no, 99% that. If you drew a side product, it would be bromination here, or bromination there, or there, but essentially this is the major product, that's what I'm looking for. If I change the game, and I add a double bond, let's add a double bond, where do I want to add a double bond? We'll double bond there, right? Oops, I'll use my NBS this time. Go ahead and pause the video and tell me what you think the answer is. If you unpause the video, you should got this as the major product. And if you also drew this, you would be right that this is the minor product, but this is still major. It's major for two reasons. One, tertiary alkyl halide, which is 19,400 times more likely to react. Although technically speaking it is resin stabilized, so there will be some amount of this, but it'll be very, very small. So if the question was draw the major product, you have to draw this one. If it says draw the major and the minor, this should be the minor that you draw rather than any other secondary alkyl halide. Don't worry about naming things that have double bonds yet. We'll do that when we get to chapter 6. Okay? So hopefully bromination makes sense to us now. It's the exact same mechanism. Actually, you know what? Let's do the mechanism. The initiation step for bromination, we'll do the example we just chose. Initiation is that, bromine, bromine. Ultraviolet light comes in and says, ha-cha! Homolytic bond cleavage to give you 2 Br dots. Br dot then, in the propagation step, sorry, I'm kind of jumping. Br dot says, hey dude, make a bond with me. Carbon says, no problem, I don't mind that. Oh wait, now I only have 7 electrons. Ah. And HBr. Right? The second step. A molecule of bromine, Br2. Kissing arrows. That's what I like to call them. I don't know if that's what they're called. That's just what I call them. I'm pretty sure that's what they're called though. Gives you your product and another molecule Br dot. That's good. So this molecule can float up here now and repeat the reaction. And what is our termination step? Termination step would be 2 Br dots coming together to give us, sorry about that, ugly, another bromine. Or it could be carbon radical coming together with bromine radical to give us the product. But now we have no more radicals, right? And of course there's one more termination step, might as well draw it. Carbon radical plus carbon radical gives us the carbon-carbon bond, big old ugly thing. And I won't ask you to name that because there's 2 cyclic compounds. It gets a little confusing. So, alright, so I think that's the end of chapter 4. I mentioned a little bit about antioxidants and also carbanion stability, so I guess I'll go through that really quickly. Right, an antioxidant is a molecule that's responsible for scavenging for electrons. So I said vitamin C is a good example. Vitamin C looks like this. So I got an OH group here, an OH group here. Those are H's that can be donated then. Carbonyl over here. We got another OH group here, another OH group here. Lots of OH's hanging out. So in the event that you have some radical species, whether it's a carbon radical or it's an oxygen radical from oxygen we breathe in the air, whatever, doesn't matter, it can make a bond to this. Right, that gives you RH, that can float around, the body can take care of that, or the organism can deal with that problem. The remaining O dot is now very strongly resonance stabilized through all these double bonds. Right, so one can go there, one can go there, one can go there, give you a resonance contributor, it looks like this. My hand is starting to hurt, so I'm going to stop drawing for now, right? So that would give you a double bond here. That would give you this, OH, double bond there, right? And this is resin stabilized through one of these going here, one of these going to the oxygen, one of them going there. I told you I was going to stop drawing, but I must have lied. So you can get that, you can get that, the H, positive charge, or maybe it's neutral, you have to calculate the formal charge, etc., right? So you can move the electron all around. That's the point of the game. So that's how antioxidants work. That's why it's good to eat chocolate and drink wine, not necessarily together. And you take care of those free radicals that are floating around. Alright, so carbanion stability is the last thing I want to mention. Right? Carbanions are carbons with a negative charge, right? Sp3 hybridized. I think in lecture I might have said Sp2 by mistake. My bad. Because of the inductive effect, it turns out that the effect of extra carbons is actually a bad thing. So if you have 3 carbons attached, right, and you have a negative charge, the inductive effect still happens, where he says, oh, you can have my electron density, you can have my electron density, you can have my electron density. He's like, wait, I got too much electron density as it is. And so as it turns out, the most stable carbanion is the one that has the least amount of carbons. It's the opposite trend than for carbocations. So 3 is the worst. Big frown. 2 is second worst. Maybe I should draw these the other way. I should go like that, right? In terms of stability. 1 is the best. H, negative charge. So frown. He's got a little bit of a frown. He's a big frown, he's a little frown. Okay, something like that, right? This is the best way to be because there's no carbons next to it, pushing electron density into his negative charge, right? You're taking electrons that are in an orbital and you're adding electron density to them. Electrons don't like to be next to each other, and so they smash into each other and raise the energy of the system overall. Alright, so that's carbanions. I briefly mentioned carbenes. Carbenes are just carbons that have 6 electrons. They're highly reactive. You're not going to see them again until we do cyclopropionation reactions. It's going to be a while. I think it's OChem 2 actually. So 6 electron carbon species, highly reactive. It's called a carbene, C-A-R-B-E-N-E. Don't worry about that. I'm just saying, hey, look at this thing, it exists. That's it. So that's the end of chapter 4. I think that's all the important stuff. You really need to know your mechanisms, right? From here on out, chapter 5, we're going to take a quick detour into stereochemistry, but once we get to 6, 7, 8, 9, 10, 11, 12, 13, all the rest of the chapters is mechanisms. You really have to know your mechanisms now because we're going to take those mechanisms and make them more complex in the end of the first semester and also in second semester. And if you're taking my class, I'm going to assume you know them, so you really want to learn them now. So the best way to know them is to look at a problem, like for example, if I just give you some structure and say, do free radical chlorination, and draw the major product or draw the minor product, right? You should be able to talk through the mechanism, say, okay, this is the type of reaction it is. It's radical. That means I'm going to form the most stable carbon radical that forms, tertiary if possible, secondary if possible, primary last. And then I'll put the chlorine where that goes, therefore I can deduce that the product should be, and then you write down the answer. That's the line of reasoning. That's how you want to solve things. That's how good you need to know it to do well on a test, right? Knowing everything is not necessarily good enough. You have to know it and know it well enough so you can answer all my questions in an hour and 15-minute period. So good luck studying, guys. Like I said, I'll be on campus at 4 o'clock on Monday. If you want to do a little bit of review or study session, we can hang out and do chemistry. It's my favorite thing. So have a good weekend. I'll see you in a few days.